Alright, so we've learned a lot about how to structure molecules and about the building blocks that we should look for in these molecules. We're going to take a little change of pace here, and I'm going to describe for you a shorthand that I hope will make your life easier, but it'll only make your life easier if you understand the shorthand. Our learning goals are to learn about simplified bond line diagrams and how they are used to draw larger molecules. I want to pose a question to you. Suppose you look up a molecule in Wikipedia, like 2,2,4-trimethylpentane, and look at the diagram below it. What on earth does that diagram mean? Is that some sort of chemical hieroglyphics that you have to interpret? Well, this is what we're going to learn about in this video, is how to actually reconstruct the molecule from that drawing. So this is a shorthand notation. I will point out it's very tedious to draw Lewis structures for large molecules. If you draw the chemical symbols of all the atoms and then draw bonds between them, I can just tell you that chemists are way too lazy to do that. So what we're going to do instead is do something that's a little bit simpler but still carries all of the meaning of a structural diagram. We're going to draw carbon-carbon bonds as simple line segments. So the end of each segment represents a carbon atom. And we're not going to draw any of the hydrogens that we don't have to. In other words, we're going to simply infer that there are hydrogens there that cause the total bonds around the carbon to total up to 4. So let's look at propane as an example. Now we've seen that this is a Lewis structure for propane, 3 carbon atoms connected together, and then 8 hydrogens connected around on the periphery of these 3 carbons. So how would we represent this using this shorthand notation? Well, pretty simple, huh? I've drawn the bonds in different colors so you could see where they are represented in the bond line diagram. And we have, excuse me, we have the following interpretation. The ends of the line segments are carbon atoms, so there are 3 of them, one at the end, one in the middle, and one at the other end. The end of the chain, that carbon has only 1 bond shown, so it has 3 other bonds that aren't shown, so it must be a methyl group. All right, so anytime you see the end of a carbon chain, it's going to be a methyl group. If there's an angle like this one in the middle of the chain, that's a CH2 group, as long as there's no other bonds drawn. All right, so hopefully when you see those, you'll begin to automatically interpret them in the correct way and be able to get the structure out of this. So here's a couple of other possibilities, and again we're going to note that all carbon atoms implicitly have 4 bonds, all nitrogen atoms have 3, and all oxygen atoms have 2. So we're not drawing the hydrogen atoms unless they are connected to oxygen or nitrogen. So that could be OH or NH2, for example. So this first molecule on the left, we've got 1, 2, 3 endpoints on line segments, so there's 3 carbons. Here's what the full molecule would look like with the same numbering system. So you can see that the carbon on the end there is indeed a CH3. The other one is as well. We haven't indicated that, but it is also a CH3. On this molecule on the right, we have a very similar sort of structure, except now we have a nitrogen in the middle, but the ends of the other ends of those segments are carbon atoms, and once again there's one at the end of the chain, so it is a CH3 at the end of that chain. Now I'm going to invite you to do the same for this Lewis structure, and for this bond line diagram, and find the Lewis structure for it and write the molecular formula. All right, so take a moment, pause the video, and see if you can do it. All right, hopefully you've had a chance to draw your Lewis structure. Hope you first counted the atoms. There are 4 carbon atoms, so we'd put them together. There's an OH attached to the second one, and the rest are all occupied by hydrogens, to fill in so that each carbon has 4 bonds. So the total formula is going to be 4 carbons. If you count around the periphery, there's 10 hydrogens, and there's 1 oxygen, so its formula is C4H10O. This molecule is actually called 2-butanol. Now let's get back to the molecule we saw at the beginning of the video, 2,2,4-trimethylpentane. Okay, we can now interpret this diagram, and let's go through it very carefully so that you can see how this is done. So I'm first going to draw the carbons that are indicated in this bond line diagram and then connect them together in the same way. So you can see, I hope, that I've essentially created the same connectivity between the carbon atoms drawn here as there are in the line segments that are drawn in the diagram. All right, now I want to count the number of bonds around each of these carbon atoms. So as I go around the periphery, each of those carbons have only one bond. The one in the middle has two. The one to the right of it has three, and the last carbon already has 4 bonds, so it can't accommodate any more bonds than that. So now we need to find how many more bonds each carbon needs in order to make a total of 4. So we would find that each of the ones with 1 bond needs 3 more. The one with 2 bonds needs 2 more, and the one with 3 bonds needs 1 more. And of course the one with 4 doesn't need any more. So all of those empty slots, since nothing else is drawn, must be filled with hydrogen atoms. So I'll leave those numbers there so we know how many hydrogen atoms to add, and here we go around the horn, adding those 3 hydrogen atoms each of those places, adding 2 to the one in the middle, adding 1 to that one, and of course none to the other. So when we erase the numbers, we now have a Lewis structure for the 2,2,4-trimethylpentane. In case you're interested, this is actually the primary ingredient in gasoline, the stuff you put in your car, and this is what people are measuring when they give gasoline its octane number. This is the molecule that gives rise to that octane number. It has a formula of C8H18, as do all of the octanes.